SMP, a SIMP method. There's also a 3D density function. There's also what's referred to as a volume of fluid method. All of them are based on kind of having this unit cell with a void defined by A and B. If A and B equal 1, this becomes a complete void. The whole unit cell disappears, okay? If A and B are someplace in between 0 and 1, then it's going to be a porous cell. If it is A and B is 0, it's a solid cell. And you can easily see how if you had a porous cell and you applied a density function to that, you would get a feel of this thing being a partial weight, a partial structure, and you could basically roll up all of these partial structures into a complete design. So the reason that these are referred to as continuous methods is because the void can literally vary any place in that range. There is no kind of set step for the void to take. It can be anything. Another group of methods is referred to as a topological derivative sensitive method, and it has this evolutionary structural optimization, shorthand ESO, and it's the one where you define your unit void. So in this case, we define a circle of, say, diameter 1, and that circle of diameter 1 is placed at every point location where there is low or no stress. And so by placing that void at all of these green locations, green being low stress, you can place those in and then say subtract and end up with the topological derivative sensitive method. So you either have a void at a location or you don't have it. You don't have a varying void at that location like in the continuous method. There's also a BESO method. The BESO method, the only thing to kind of remember on that is you can actually add material. So this void doesn't have to be a void, it can actually be a volume that gets added onto this. So if you need to kind of bump out and add additional material, the BESO method is the one that can actually extend the geometry beyond its design shape. Another very, very important method is referred to as the truss method. We'll be talking about that on Thursday. The truss method is the oldest topology optimization method. It's been around forever. Basically, the structural civil engineers developed this optimization scheme. So we'll talk about that on Thursday. Excuse me. And there are other methods, but those three categories, the continuous, the topological, and the truss methods are the ones that you need to kind of, as you read these articles and try to understand what's out there, you need to kind of hang on to that information. What software tools exist for doing topology optimization? Well, the one that we use in this class comes from Altair Engineering. It's a combination of HyperMesh, OptiStruct, and their solver called Radius. If you look at the examples on this image, you'll notice that part of the landing gear, the before condition had lots of red. If you look at the after topology optimization, you'll notice that the red has been significantly reduced, which is a good thing. If you look at the example on the right, you can see kind of the base original design, and you can look at the optimized design and realize that they haven't sacrificed any safety. The stresses are as low in the part on the right as they were on the part on the left. There are other packages. Just one of them that we'll name is a combination of Patran, Nastran, Atoms, and Construct. They can do the same thing. If you look at the pictures on the screen, you'll notice that those are done inside of what? Okay, so Patran, Nastran, those guys have locked arms with the folks at Dassault, CATIA, and they basically embedded a topology optimization approach into the CATIA system. And again, the combination of turning out lots of charts showing you the stress levels, okay, and being able to map out a better designed structure is what topology optimization is about. So in the time that's remaining, we're going to try and talk through a number of case studies just to help you gain an appreciation of why this is so important. Many of the students from BYU and many of the students that at the remote schools that we're working with have had opportunities to actually, after this class, go into industry and work topology optimization problems because of the basic introduction and understanding gained in this class. It's a very, very important thing to Boeing. Boeing on the 787, there wasn't a single structural part of that airplane that did not go through topology optimization. Many of the parts that are put inside of cars these days are taken through a topology optimization process. And so it is becoming a very significant and a very important part of upstream design. You don't see them doing topology optimization once everything's locked in, but in the conceptual and preliminary space, they're doing lots of optimization. What were the challenges on the F-35? Well, the F-35 came in 3 variations, right? What was the CV variation? That was the carrier, so it was designed to take off of carriers. What is the CTOL version?
Air Force version.
It is the conventional takeoff and landing, so it's the Air Force version of this. And what is the STOVL version? Short takeoff and vertical landing. Okay? So of these airplanes, which one do you think has the kind of the most significant requirements on it? Bottom one, okay? This one. And it's because of the vertical landing piece, okay? So basically, when they sat down to work on this plane, they said the weight reduction on the short takeoff and vertical landing variant design was the biggest deal. Reduce the weight of that. Consider every part with individual part weight reviews. Consider every system with system weight review. And so the thing that drove the design of that variant was weight. They had to get as much weight out of that thing, but still have a very safe airplane. The last thing they wanted to do is say, well, if we can save weight on these kinds of things, can these parts go into the other 2 variants and likewise have a lighter plane, because a lighter plane means better performance, slower or less fuel burn, okay? So this is basically the process that they went through. They had a base part from a previous F-16, F-18, but a previous part. They said, here's what the part on our last design kind of looked like. We need something that's better than that. So they took the base design, they mapped out a design space, so they grew the thing and said it needs